July 2026. On the slope of Mauna Loa, instruments register 429.12 molecules of carbon dioxide per million molecules of dry air. The number seems almost negligible, less than 0.05%. But it has already moved far beyond the corridor within which the atmosphere remained during the last 8 glacial cycles. And now this small impurity may determine an event that was supposed to occur tens of thousands of years from now. We are accustomed to discussing climate on the scale of a season, a generation, or the end of a century. The Earth has a different calendar. Its hands move so slowly that over all of written history, they have barely changed position. One is linked to the planet's tilt, another to the direction of its axis, and a third to the shape of its orbit. Together, they decide whether snow will survive the northern summer, whether an ice sheet will appear, and whether the ocean will drop by 100 meters. But a new variable has entered this ancient mechanism. How much time remained until the next major glaciation without humans? Can we truly say that we have canceled it? And how can the emissions of a few centuries alter the climate scenario for 100,000 years ahead? First, confusion about words must be cleared up. An ice age is not necessarily a world entirely locked in ice. Geologists call an ice age a long interval during which permanent large ice sheets exist on the planet. In this sense, we are still living inside an ice age. Greenland and Antarctica have not disappeared, and the cold advances of ice and warm pauses within it are called glacials and interglacials. Our pause, the Holocene, began roughly 11,700 years ago. The next glaciation does not turn on by a timer. A harsh winter alone is not enough. In winter, snow can cover a huge territory, but if it melts completely in summer, there is nothing for a glacier to grow from. The turning point begins where part of the snow survives until the following autumn. A new layer is deposited on top of the old one. The lower snow compacts, turns into firn, then into ice. The light surface reflects more solar energy, the air above it becomes cooler, and the next snow gets an extra chance to persist. A small remnant triggers a large feedback loop. Therefore, for ice sheets, what matters is not the planet's average temperature, nor a January record cold, but the energy of the summer sun at high latitudes of the northern hemisphere. In the north, there are extensive continents where snow can accumulate. At the same southern latitudes, the ocean dominates. Thus, the fate of ice across the entire planet becomes especially sensitive to what the short northern summer will be like. NASA groups the causes of changes in this summer light under the name Milankovitch cycles. The first cycle is the tilt of Earth's axis. Over the last million years, the angle has varied from about 22.1 to 24.5 degrees, and the full rhythm takes about 41,000 years. Greater tilt amplifies seasons and adds summer light at high latitudes. Lesser tilt makes the northern summer cooler and helps snow persist. The second cycle is precession. Earth's axis is not only tilted but also slowly traces a circle, like the axis of a spinning top. At the same time, the orbital ellipse itself rotates. Their combined rhythm averages close to 23,000 years. Because of it, the summer of each hemisphere shifts between the near and far parts of the orbit. Currently, Earth passes perihelion in early January and aphelion in early July. According to NASA, the distance difference is about 5.1 million kilometers, so the January solar energy flux is about 6.8% stronger than the July one. For the northern hemisphere, this softens the summer peak. The third cycle is eccentricity, the slow change in the shape of the orbit from nearly circular to slightly more elongated and back. One of the main rhythms takes about 100,000 years. By itself, it only weakly changes the annual amount of energy received by Earth. But eccentricity determines how large the difference will be between the near and far points of the orbit. In other words, the weak hand regulates the strength of another hand. For a long time, this created an inconvenient paradox. In the late Pleistocene, major glacial cycles repeat roughly every 100,000 years, as if following eccentricity. But the direct energetic effect of eccentricity is too small to build or destroy a continental ice sheet on its own. The climate seemed to listen to the quietest metronome. In February 2025, Stephen Barker and his colleagues published a paper in Science about the different roles of precession, tilt, and eccentricity. Instead of trying to assign one dominant cycle, they compared the shape of glaciations and interglacials with the relative position of all three orbital motions. The authors concluded that the onset of deglaciation is more strongly linked to a precession peak against a background of increasing tilt, and that tilt is especially important for reaching the interglacial peak and the subsequent initiation of ice. Eccentricity in this picture does not act as a separate cold button. It changes the amplitude of the precessional kick. When the orbit is close to circular, the difference between its far and near segments is small. When it is stretched more strongly, the same orbital season turn more noticeably changes the summer energy. The Science article shows that the rough shape of all cycles over the last 900,000 years can be largely reconstructed from orbital phases. This is a strong result, but not the final formula for climate. The authors explicitly leave room for internal feedbacks and verification with new data. How is the shape of cycles that no one could observe in their entirety known at all? Part of the record is stored not on land, but under kilometers of water. Microscopic marine organisms build their shells from ocean material. The ratio of oxygen isotopes in these shells depends on water temperature and on how much of the light isotope was locked in continental ice. After death, the shells sink to the bottom. Layer by layer, the sediment turns the ocean floor into a long climate record. This record is not like a ready-made thermometer. The age of the layers must be determined, the influence of temperature separated from ice volume, and the local signal compared with cores from other oceans. But when independent archives repeat the rhythms of obliquity and precession, the orbital hypothesis ceases to be a mere coincidence. It was marine cores that helped the work of Hayes, Embry, and Shackleton in 1976 turn Milankovitch's calculations into a testable climate history. There is also a more Jiguan scale. Kurt Lambeck's team assembled for a paper in PNAS about 1,000 observations of ancient sea level and corrected them for crustal motion. The reconstruction shows, at the peak of the last glaciation roughly 21,000 years ago, the mean ocean level was about 134 meters below present, and the volume of land ice exceeded the current one by roughly 52 million cubic kilometers. This is not just a cold version of a familiar map. Coastlines were different, shelves became land, and the weight of ice deformed the planet itself. Then melting returned water to the ocean. According to Lambeck's calculations, the main phase of rise between 16,500 and 8,200 years ago proceeded at an average of about 12 meters per millennium, but individual pulses were significantly faster. It is important not to mechanically transfer this figure into the future. The geography of glaciers, ocean temperature, and the rate of feedbacks differ each time. The past provides physical limits, not a ready-made scenario. The second half of the glacial mechanism is hidden in air bubbles. In Antarctica, snow did not melt, but accumulated for millennia, compressing older layers beneath it. Air became sealed in the ice. In 2008, Dieter Luthi and a large international team published in Nature data from the EPICA dome sea core, extending the direct record of atmospheric CO2 to 800,000 years. Over 8 cycles before the industrial era, the concentration lay roughly between 172 and 300 parts per million. The ice shows a close link between carbon dioxide and Antarctic temperature, but this link does not mean that climate had a single control knob. Orbit changed the geography and seasonality of sunlight. The warming that began reorganized the ocean and the carbon cycle. More CO2 entered the atmosphere, and the greenhouse effect spread and amplified the change. During cooling, the chain could work in reverse. Orbital cycles set the timing, while ice, ocean, vegetation, and carbon determined the scale of the response. About 800,000 years ago, the system changed its rhythm. Before that, glacial variations more noticeably followed the obliquity cycle of roughly 41,000 years. Then glaciations became longer, deeper, and approached a step of 100,000 years, even though the orbital parameters themselves did not acquire a new schedule. NASA notes that there is no clear, single explanation for this mid-Pleistocene transition yet. Among the hypotheses are a gradual decline in background CO2, erosion of loose soil under glaciers, and nonlinear behavior of large ice sheets. The new orbital scheme explains the order of many later cycles, but does not turn the entire system into a frictionless clock. Now, let us return to the number atop Mauna Loa. NOAA's Global Monitoring Laboratory reports that the mean CO2 concentration in July 2026 was 429.12 parts per million. This is a preliminary monthly value from a single high-altitude station, not a global surface average. But the comparison of scales remains fair. The modern value is roughly 43% above the upper bound of 300 parts per million in the pre-industrial 800,000-year EPICA record. It is easy here to draw an overly dramatic conclusion. Humans have canceled the Ice Age. Science speaks more cautiously. First, the next natural glaciation would not have been obliged to start soon, even without industrial emissions. The current orbit is nearly circular, so the coming minima of northern summer insolation are relatively weak. Second, today's CO2 concentration and the total amount of carbon emitted are different indicators. Part of the carbon is absorbed by the ocean and land, part remains in the atmosphere for a very long time, and the balance changes over time. In December 2025, Christina Kaufhold and co-authors published in Communications, Earth and Environment an open-access study on the timing of future glaciation. They coupled a climate model, a carbon cycle model, and dynamic ice sheets and ran simulations 200,000 years into the future. In the preferred scenario, the natural onset of the next glaciation occurred approximately 52,000 years from now. But under a different assumption about the balance between volcanic carbon input and its removal by weathering, the timing shifted to roughly 126,000 years. This difference is an important part of the result. The deep future depends on processes that are not perfectly measured today. The model also separates scenarios by cumulative emissions. Historical emissions already released about 500 petagrams of carbon, in the author's estimate, by themselves likely did not push the model start beyond the natural threshold of about 52,000 years. At cumulative 1,000 petagrams, roughly twice that amount, ice initiation was delayed by another approximately 50,000 years. Even in scenarios up to 5,000 petagrams, the model typically returned glaciation within the next 200,000 years. This is not a calendar record of the future, but a set of physical experiments with explicitly stated assumptions. A petagram of carbon is 1 billion tons of carbon itself, not of carbon dioxide as a whole. This unit describes cumulative emissions, whereas parts per million describes the fraction of CO2 in the air at a specific moment. There is no constant conversion factor between them for all time. The ocean, soils, and plants continuously take up and release carbon. Two worlds with the same present-day parts per million can arrive at different states 10,000 years later if they receive different impulses and distributed carbon differently among reservoirs beforehand. The authors therefore calculate not a single trajectory but a family of trajectories. In one, geological sources nearly balance carbon sequestration and the concentration stays near the pre-industrial level for a long time. In another, chemical weathering slowly outweighs the input, CO2 declines, and the threshold for ice growth is reached earlier. The spread between 52 and 126,000 years arises not because the orbit is hard to calculate. Earth's position is known far more precisely than the future behavior of its carbon reservoirs. Why is the imprint of a short industrial era capable of lasting so long? Atmospheric CO2 has no single disappearance time. The fast fraction is taken up by plants and the upper ocean. Another part goes into the deep ocean over centuries. On the longest timescales, carbonate dissolution, sediment formation, and chemical weathering of rocks come into play. Therefore, the impulse does not decay like a drug with a simple half-life. A small residue can persist precisely at the time when the orbital calendar again creates conditions for snow that survives summer. This is less like a pencil mark that gradually fades and more like the redistribution of water among connected reservoirs. The level in one vessel may almost return to its previous state, even though the whole system already stores a different stock and reacts differently to the next perturbation. Therefore, the question, how many molecules will remain after 100,000 years, is too narrow. What matters more is the state in which the ocean, ice sheets, soils, and rocks will be at that time. But it does not follow from this that emissions are a useful insurance against glaciers. Compare the timescales. A possible natural onset of ice is tens of thousands of years away from us, while the consequences of rapid CO2 growth unfold already on the scale of a human lifetime. You cannot extinguish a distant hypothetical threat by intensifying a close and observable one. Moreover, a new glaciation is not a sudden white wall. Its onset would take many generations and would leave measurable signs. Nor should one promise that we have permanently broken the cycle. The orbit will continue to change tilt, axial direction, and eccentricity independently of human history. Carbon will move between the atmosphere, ocean, rocks, and living systems. Ice sheets have thresholds and memory. Ocean circulation can alter the precise moment of initiation. On a timescale of 100,000 years, uncertainty is not a weakness of science, but an honest description of many slow interactions. The most accurate formulation sounds less loud and is therefore more important. Humanity has not turned off Earth's calendar. It has added a new hand to it. Orbital cycles still set windows of opportunity, but the composition of the atmosphere can close some of those windows. For the first time, one species has changed the condition of a problem that previously was solved only by the motion of planets, the ocean, ice, and rock. And this changes the meaning of the word present. A molecule of CO2 released today does not have to remain in the air for 100,000 years to affect that distant climate. It is enough to alter the chain of exchanges, ocean temperature, ice volume, and the state of the carbon reservoirs from which the next stage begins. In a system with memory, consequences live not only in the original cause, but also in the new state of the entire system. Imagine three clock faces. One completes a revolution in about 23,000 years, the second in 41,000, the third in about 100,000. For most of the time, their combinations do nothing dramatic. But sometimes the northern summer weakens enough, snow remains, the white area grows, and the ocean and atmosphere amplify the push. Now, a fourth dial is working alongside, the carbon one. Its position was changed by us, and the speed of return is determined by the ocean, life, and geology. On Mauna Loa, the instrument does not see a future glacier. It merely compares the air with reference gas mixtures and outputs a number. But 429.12 is simultaneously a measurement of the present and the initial condition of a very long calculation. In the ice cores, there is not a single pre-industrial cycle with such a start. Therefore, the past gives us the mechanism, but no longer provides an exact copy of the future. The glacier calendar has not disappeared. Its pages are still turned by celestial mechanics. Only a note has appeared in the margins, made by civilization, and it may outlive cities, languages, and states. The main question now is not whether the ice will ever come. It is how far into the geological tomorrow the decision made today will reach. This is the channel MIR. Subscribe to Together, analyze the processes where human time meets planetary time.